So thank you for making choices, and we do see. Oh, okay. Alison, first choice. Let me make it also. Alison, second choice. And Sibyl also wanted this one. Okay, so projects themselves are doable in one class, but we need to spend I probably need to go and steal from another class. So we need 3 to get additional background, because things that you already became experts in may slightly vary from project to project. So one can plan on, if noise will continue, I will just go and borrow another piece of equipment. So in simplified way, we are running the same code, and the difference is only to selection of a potential, but depending on the specifics of the system, one should focus on different observables and use different parameters. Also, if one is looking on molecular motion instead of electronic, one needs to change parameter of mass and time scale. And this sounds very easy as we speak, but without special preparation, if one would try to rerun the code with different parameters, it could be sometimes discouraging, and the code may work not as you expect. This, if you have experience in programming, you know that 10% of time is actual coding, and 90% of time is debugging, and one shouldn't be discouraged if the code is running in a different way. It's still better than level of uncertainty with deriving equations, but there will be specifics. So I'll cover some general aspects, and if you worry, if you believe that last couple of weeks of semester will be really busy with other exams, you can start doing project like starting today or starting this night, and send me emails. I'll assist to speed up the process. But in fact, everything can be done in the, like, if we all agree on setting up a makeup lab on the week of Thanksgiving, we can complete projects during this makeup lab on Monday. So I will plan on for everyone, and for recordings, doing maybe a little slower than needed, but focusing on some aspects. But there will be guidelines and criteria of success, and you can go ahead, not waiting for the rest of the class. Okay, so there is a substantial number of class attendees who decided to it's not that I like watching myself. I just want to bring in the screen and board. Okay, sounds like this. So there are at least 3 class attendees who, maybe 4, is interested in the first section, and I will cover principles how one can model it without ab initio help. And even if you do different project or redecide your choice later, which is still okay, it will be something general and useful for the future. For those who are very energetic and impassioned and have selected the section C, I have shared here a couple of codes that one can try running before we get the background, or just wait. I will try to go to these modifications of the codes as soon as possible, but I can promise that we will do it today. And yeah, so the plan is to speak about A and C today, and B is in some sense easier. The running of the code itself needs almost no modification. The question is more how to theoretically process the outcome of the code. So the observables for chemical reactions and their interpretation are slightly different than the analysis of other codes. Okay, and I have noticed that there were 2 class attendees who selected exotic things from the bottom. So Joe selected Bohr model with Bohr model, and Joshua selected nuclear magnetic resonance. So I did send some preliminary codes probably to everyone, but if you are on the link and you are Joseph or Joe, feel free to try these codes and develop your questions, how it works or why it is not working, and then by speaking one-to-one, you'll go quicker. All codes are welcome to use by everyone, but we just need to some organized way to deal with them. So the models of the electronic motion, the one-dimensional potential that attracts electron inside one atom. So of course, one-dimensional problem is one-dimensional formulation is far from reality. To get exact answers, one needs to do 3 dimensions. But in the frame of this class and in the frame of only months remaining until the end of semester, we can do only one-dimensional. So we need to design a potential that will approximately mimic attraction of an atom. I will use parameters for silicon, which is like part of semiconducting tools, and I will just offer focus your attention on the part of the code where potential where the potential for the atom is set up, and after we do a little exercise with, we'll speak how one can replicate and model crystalline lattice as a assembly of several atoms on a regular distance from each other. So if you have your MATLAB open, we should be able to run the same code that you have presented last Friday. And I will suggest specific portions of this code we need to focus on. So let me attract your attention to the line 37. So there is no big science. It's more fitting the attractive potential that describes atom, but by energy from ionization energy from electron localized on the atom to be completely removed, right, from the top to the bottom, and the width parameter. It is not and the center X equilibrium. So there are parameters for the depth of the well. There is a parameter for the width in atomic units, and there is a X equilibrium. So the equations that we are trying to build, it is similar to the Gaussian, inverted Gaussian, but it is a little flatter in the center and a little sharper on the edges. So let's reconstruct what is written here. So it is so if you have in the exponential squared in the denominator, it will be like Gaussian, but in addition, we have this width parameter. No, it is. So let's try to plot this v of x, and then quickly run dynamics by setting initial position of the wave packet right in the center of this well. So the you see the depth is like minus 0.42 in atomic units, and it is shown it's as deep as here, and the width is around 2. It shows how deep is this potential. And most important thing is that after defining this function, we set the potential, the variable for potential v is equal to this artificial function, and later on, anywhere where v is defined, it is commented out. So please try doing this little exercise, and I will be back in a minute, just trying to bring better microphone so that we have less noise. The test. Less noise, right? Okay.
I didn't see what did you comment out at the beginning to make it.
No. The variable, the function v test is defined. You do not need to change anything. Just write v equals v test, and then scroll several lines and see that it is the last definition of the variable v, and there are no other definitions competing with it. You're going on your own schedule. That's good. That's good. We will get there. You are.
So I tried plotting just v, and then I get.
Did you type v equals v test? And then plot v. Okay, and right now you did it in the command line, but you need to change it in the body of the code.
Put it here or put it at.
Maybe the last somewhere there. Last time you referred to variable v, and like you can do it right here. V equals test. V test. Yeah, and then just check for next 20 lines if there is no competing definition. Yeah, put percentage in front of it. And then save and run. So it is expected that you see that this potential traps probability, and instead, at least portion of it. So instead of going somewhere, it is electron is attracted to ion and staying there. So let me quickly stop sharing and make sure that. Lola, are you ready to do this little exercise, or you just connected?
Yeah, I'm ready.
Okay, can you share? Oh, I need to make everyone co-host. Adam co-host, yes. Sibel co-host, yes. Okay, and I want to see your figures, not the code.
Yeah, I'm not sure that it ran yet.
Or in the code, let's scroll to the line 50. Scroll up.
Here.
Okay, even higher. Scroll up.
37 here.
Yes. So after 38, make new line. Right here, make new line and type V capital equals V test.
Like this?
Yep. Semicolon. Semicolon, and then scroll down to erase any. Scroll slowly, not colon but semicolon. Point and comma. Yes, yes, exactly. Slowly scroll down. So line 61. Line 61 should be commented out. Put a percentage in front of it. Okay, save and run.
I can run it now.
Yes.
Okay.
And if you can bring the image to the screen, would be great. Right now we see only your text or the code.
Oh, okay. I need to.
Or stop sharing and then start sharing over again, but the whole display. Yeah, pause, press any key. Wow, what is going on?
Say something about line 178.
Which code? No, it's a good code.
Am I sharing? Am I using the wrong?
No, you're using the right one. Can you please bring up the command line, command window, Control C, Control C. You probably did run Control C. It looks like you tapped triangle to run the code several times. Control C once again. Control C. Okay, good. Plot, open bracket, uppercase X, comma, uppercase V, close bracket, comma, V for potential, comma, V.
Oh, V.
Yes, close bracket, enter, bring up the figure. So it's a potential of a single atom with parameters used for silicon. If it is bigger, an atom with bigger ionic radius, then one needs to use bigger width. If it is more oxidative, like oxygen or chlorine, one needs to use bigger E well, have it deeper. And the error came because you run several times, it just several layers on top of each other, but I think you're doing good. So you can stop sharing and we'll talk to the next.
So what line of the code do you have to change when you want to change the?
Oh, you did everything correctly. If you run it once, not several times, it should work.
No, you said this is for silicon and that, right? That's what you said.
Yes. Lines before 37, the lines that define parameters E well
Okay.
and width.
So those are the ones that you have to change when you're changing between
Right
atoms.
now you do not need. It's only information.
I'm just asking.
Huh?
I'm just asking. I'm not trying to change it.
Okay, it's good. Yes. Joshua, would you like to share screen? Okay. Did the code work? If you did you run the code and did you saw? Can you tell by words what you see if you run it? Or just run and show?
Yep. All right.
So what do you observe?
Yeah, notice that it's like the wave on top isn't moving too far away from the trench.
Okay, yeah. So it is trapped near the atom because atom attracts electron. Excellent. Thank you. You can stop sharing. Adam, would you like to share screen?
Sure. Yeah.
Okay. Okay, I saw it. I see it. It works. Can you erase this one and just bring something? Maybe, yeah, just. Excellent. Thank you. You can stop sharing. Everything looks good. Sibel, would you like to share screen? Okay, yeah, I see everything is great. Thank you. You can stop sharing. And I will be sharing back. So the actual materials typically consist of, like, molecules, and solids consist of more than one atom. So we need to set up interatomic distance. Here we call it AZ, and then we can add together several of such potentials, but they will be offset from each other by number n times interatomic distances. Nate and Wyatt, does it make sense? So just offset n times interatomic distance and do another potential and add them together. And we do it for the negative and for the positive. So now I want to use, so it is accumulated in the variable VV, and now I want to set V equals VV. So save as, it's something like 11 silicon atoms. If I run it, so you see there are several potentials, several atomic potentials, and they represent a solid. And since they come closer to each other, the electron can tunnel from one atom to another. So it's main principle of solids, metals, and semiconductors. Although there are individual atoms, electron hybridizes and travels from one atom to another. Do you see it? So let me bring up the piece of code and then go over. And to make them all equal, I add eval here to have the same atoms. By definition, it was number 2 here to show interface between two different materials, but let's do more homogeneous. Okay. And it's multiplied by 2, but you can replace 2 by 1. Okay, yeah, excellent, thank you. So I'm going to stop sharing and ask everyone to do it one by one. Lola, would you like to share screen? Thank you. So after this, like maybe in line 45, empty line, please type V equals VV and semicolon. Now save and run. So push a space button or any button. Okay. Let's see what's going on. Yeah, let me share.
It's line 58. I don't know if she had go to line 58.
Here.
Okay, you put then it should have worked.
There is a chance that occasionally, if like a cat walks on a keyboard, there are some uncontrolled errors. So maybe it's if I will email the original code, or you can take the original code from the email and start working with it, because maybe by some modifications.
Oh yeah, that's true. Because I took it from the last class, so yeah, it's not the original one.
We can debug and find what was wrong, but it may take
Would take time. Yeah. I mean, somebody else can go. I'll just pull up the original one and change it.
But before, yeah, okay, yeah, please try doing it. Joshua, would you like to share screen? Okay. So you see how it distributes from atom to atom, right? And interestingly, it primarily resides in the area where we have atoms, and it doesn't go too far to the area beyond, right? Yeah, very good. You can stop sharing. Sibel, would you like to share screen? Okay, everything is perfect. Thank you. And in your case, a portion was away because initial momentum was high enough to for electron to jump out of the box.
Yeah, exactly.
Adam, would you like to share screen? Yes. And in your case, it didn't jump out of the box because momentum was had smaller value. P naught at the very beginning. It's one of the first ones. P naught 0.25. Yep, very good. You can stop sharing. So I will share back. So there is a very broad class of problems. I'm going to tell something that can be sufficient for a project, but maybe whoever selected this area will go much further than that. So I'm going to give some general introduction to charge transferred interfaces. So by now you can do some basic level modeling of one-dimensional molecules and solids, right? And if you have seen the previous version of the code, it had deeper potentials on one side, right? If you look into Wikipedia, which you do not need to do, but you kind of, you do not trust me, or if you have some time to invest, there is a p-n junction, which is a key for solar panels and all electronics and diodes. So when two semiconductors of p-type and n-type are interfacing each other, so p-type is n-type is negative, where there is an excess of electrons. P-type is positive, whereas the lack of electrons, or holes with positive charge. This is obtained not by injecting additional charges, but it is set up chemically through so-called doping process. So if you look into the periodic table, like I'll focus on only part containing silicon. So carbon. What is to the right from carbon? Nitrogen, right? Oxygen. What is to the left from carbon? Boron, right? What is to the bottom from silicon? Tin, I think, or telluride. Let's look. And now we also need things on in the remaining cells. Germanium. You're correct. Yeah, thank you. Germanium. And what is to the aluminum? Okay, thank you. Aluminum and phosphorus. Yeah, so it is enough. So what is the octet? How many electrons are on silicon? Yeah. How many electrons are on phosphorus? 5. 1, 2, 3, 4, 5. How many electrons are on aluminum? 3. So if we take silicon from crystalline lattice and replace it, not all, very few, by phosphorus, it will contribute one more electron, or as many more electrons, as many more phosphorus atoms in the crystalline lattice. Since it has similar ionic radius and it is either, it's very similar to silicon, lattice will stay the same, but it will be enriched with electrons. If we replace, substitute silicon with aluminum, nearby it will be lack of one electron or as many electrons as substitution as it did. And due to this imbalance, the potential with lack of electrons will be deeper, and potential in the area with excess of electrons will be taller. So it will be naturally favoring to go from one area to another, or if we apply voltage to go to left from the right or right from the left, it will this junction, this interface will respond to external voltage in a different way. So it will happily go from P region to N region if we add voltage, but it will not go from the P region to N region. And illustrating this mechanism is one of the possible things that one can easily do, just doing nothing else but running the code as we have now. So let me do a little illustration, and we can do some things. Oh, it was not shown. Those who are online should request me to focus. So now you see, if you want to, you see this little illustration. So if we model it by modifying the width, and right now we are not up to exact numbers. We just need to model that at one side we are deeper and at another we are taller. So we can do this modification, and it will be a model of p-n junction in semiconductors. And there is one additional thing. So if we do linear ramping, it means the potential will be increasing. So everything will be tilted, either positive or negative way. And so I'm doing this change to implement electric field. Then I am saving. Remove all this. Save and run. I was too ambitious and it completely moves everything to one side. I put too large of the field. Redo it with being more humble. Save and run. Okay, so you see there is a little tilt to overall potential, and it moves. It makes the electron to move from the p-doped area to n-doped area, which otherwise it doesn't want to do, right? So you see most of the electron density is in this area, and without field it will settle here. With field we can mandate it to go opposite, and to go in the if you sweep if you change the sign of the field, negative, save and run. So it will naturally go into the direction where it wants to go. So it's principle of the simplest electronic device at diode, right? So voltage can make current go in one direction and cannot it to go into the opposite direction, with IV curve being like Ohm's law when we go from the P to N, and no, so this is current, this is voltage, and when voltage is opposite direction, it just no current, right? So deviation from Ohm's law. So this model is illustrating principle of diode, and one can give some more quantitative things, quantitative details. I'm not going to check, hoping that you can run this little exercise, but I want to bring your attention. And now I'm going to tell something universal that will be useful for majority of attendees. Maybe, so we have total 9 attendees. So for 7 out of 9 for sure. What are those probability, and how does it deal with the fact that electron goes to one or another part of the simulation cell? So I'm going to save this image and then repeat. Repeat this experiment with swapping sign once again. Save. Run. So I'm going to look onto these figures and explore how they are depending, how they respond to the change in the electric field. or to the change in the potentials. So we already started discussing that it is it can be related to probability of the yield of the reaction, right? But here we are talking about electron transmission. So in both, they're quite similar, but here the orange line is like 31%, and here about 35%. So the change is not dramatic. But if we keep increasing field, we can make it to be more or less vivid. So maybe it's not absolutely the best example, but to save time, I'm going to focus attention of everyone on the piece of the code that generates these figures and explain what it is, because it will be a universal observable that we did miss discussing during your presentations, just because we were rushing. Yes. PL3 and PR3. So I'm going to do another figure. What? PR3. Oh, yes, it should be accumulated. It's an instantaneous value. I need averaged PR3, yes. And if I plot their sum, EVE PR3 plus PAV, you see their addition is always equals 1, right? Because wave function is normalized. So if we look onto our model, and this observable will be universal all the time. So it splits simulation cell on two sections in the middle, and then integrates area under the probability distribution in the left and in the right sides. So if we integrate it completely from lowest left to highest right, it will be 1, right? And here we are integrating halfway. So it will be probability that electron in the left part of the simulation cell. Here it is a probability that it is in the N region of the semiconductor. And here PR, right, probability, right, will be probability that it is in the P-type semiconductor. But same definition, same observable will be used for analyzing chemical reactions. So the same as with other variables, we are computing instantaneous value. So we integrate from 1 to x2, and x2 should be defined as a midpoint of the simulation. And if by some reason you need split it not literally in the center, more to the left and more to the right, the investigator who is doing the research can do it. And then we integrate from beginning to the center, and then from center to number of points, right? So just integration, and those will be instantaneous values. But if you do want time dependent, we need to accumulate data into the longer array that one can either plot or save into the file for later plotting. So let me invite you to, although the code plots the things automatically, let me invite you to reproduce this or similar image, and I'll make a circle and chat if something doesn't work. Lola, may I ask you if you have downloaded started the original version of the code?
Yeah, I did, but something is still not working.
I will get back to you in like 3 minutes after visiting Nate and Wyatt.
Okay.
Okay, yeah, excellent. Okay, great.
So
Yes.
when you just run it,
Uh-huh.
it does 2 lines at the top and 2 lines at the bottom because it's doing both the
Methods.
threes and both
Yeah.
the second method and third.
Mm-hmm.
Okay.
And we thanks to Joshua, we know that third method is more reliable. But just in case we are doing second, and if both methods coincide, it's kind of encouraging news. And if they diverge, it gives, although we use only third for actual observables, it gives us a sign that something is suspicious. Typically, method 2 and method 3 start diverging if amount of grid points is insufficient. If we use too large time step and there is a big accumulation of error. So if this pairs of lines start diverging substantially, it is a reason to just hold on and analyze what is less than optimal. Lola, would you like to share your screen? Okay. And is it all the code that was already changed, or you downloaded it anew?
Okay, from this email.
Okay, from the email. Good.
Yeah.
And how does it run? Can you run it and see and show what happens? Or if it did run, maybe just show the figures.
This was like.
Is it something is going strange? This probability 10 to the power 1/200 is not realistic. So
yeah, I feel like some things I needed to be changed because I picked it from the email. So
did you download the code from the email right now, or you are keeping working with the same code you were changing before?
No, I picked it from here, this email.
Okay, let's. So you downloaded it right now, right?
Yeah.
And can you please show how it runs? Which errors does it bring?
Doesn't exactly give any error.
Okay, let me request control and just do a couple of experiments, if you permit. Let's download to save. Now let's go to MATLAB. We are in different directories. Can we come to the same directory where you saved it? Okay, good. Yeah, thank you. It's enough. It's enough. So yes. Figure 7. Yes, something is. We are using the same. You're using the same codes as everyone else, and it gives an error. Maybe it's difficulty with installation of MATLAB. Let me offer a quick fix, so it shouldn't take time of the class. And if it doesn't work, we will talk more one by one. Would you please bring a browser up front? Okay, open new window where I can type. Okay, yeah, thank you. So NGSU Ccast MATLAB. So it will request your password on your cell phone.
Okay.
And after you approve, it will bring this page to MATLAB on Ccast.
Looks like nothing is going on the page right now.
Okay. Maybe try to do the same thing on the other browser. So instead of Chrome, try Firefox or but it should be solvable. We need to go forward with the class, but I will get back to you again in like a few minutes. So look for CCast, MATLAB, and DSU, and it will give a link to run it online on the server.
Okay.
Yeah, thank you. Joshua, would you please share screen? Okay, excellent. Yeah, you can stop sharing. It's great. Sibel, would you like to share screen? Okay, excellent. Thank you. You can stop sharing. Adam, would you like sharing screen? Okay, excellent. You did great. You can stop sharing. Now I will share it myself. So I'm going back to the area of code where one defines the potentials. Okay. Do you allow me to erase those? So, in addition to interface between two semiconductors, there was so it's around 90s. from 90s to 2000. So there is a not novel but still fun activity. Humankind needs electricity from sun. One needs solar panels. One can right now you see this bluish silicon panels. They're blue because the silicon is covered by silicon nitride, which has a blue color. But it's not ideal. There is an effort to find better materials, and there is a lab ready for that can be offered for experimental part of PChem or even in high school demonstrations, where instead of two semiconductors, one prepares solar panel by interfacing two different pairs of material. One material, which is electron acceptor, so analog of P-type, is titanium dioxide, whitish powder, and instead of n-doped, where electron is coming from, one uses dye, organic molecule that absorbs light and is able to donate an electron. So semiconductor part is titanium dioxide, and dye is a dye. So therefore, it is called dye sensitized solar cell. The high school lab, well, we are not in the experimental lab, therefore I'm not doing demonstration, but I did it just for fun. So one takes conducting glass, which is indium tin oxide. It uses only as a substrate. Then puts powder of titanium dioxide and bakes it with torch. So it is conducting stuff covered by the specific semiconductor. And then the next step is we can even, did you hear about it ever before? Anyone can guess how one deposits dye, assuming that it is available in high school? Anyone online is welcome to speak if you've heard about it. No? So one takes raspberries, squeeze them, and just pour juice on the surface. So raspberry juice. And then one uses another indium tin oxide transparent glass. And then one uses clips as one connects the paper just to squeeze them, to press them, and another just little contacts that looks like a little crocodile to left and right side, and connects it either to a little lamp or to a voltmeter or ampere meter. And then one starts shining with a flashlight or brings it to the sun, and it does generate electricity. So at the time when it was designed by Michael Gresland, in some circles he was considered as a candidate for Nobel Prize because he did show a way to escape from semiconductors, at least partially, and he did several examples when one can. Well, there is in addition to raspberry juice, there is also electrolyte for mix of potassium iodide and I2 to shuttle charges, but it's technical details. The actual process is raspberry juice between titanium dioxide. So upon shining light, the molecule is getting excited and electron becomes loose, and it can be transferred to titanium dioxide, and then if it is connected to terminals to close the loop, current flows across. The efficiency of such solar cell is like 30 times less than industrial silicon, but it is new direction, and later on it did inspire a lot of new materials used in space. So it's there are hard semiconductors, there is a organic photovoltaics based on conjugated polymers, and it's a niche in between. And since our humankind is looking, it was on the radar, and still right now, it is a bridge between world of organic molecules, which is chemistry, and semiconductors, which is physics. So in some sense, dye-sensitized solar cells is exactly physical chemistry or chemical physics. It's interface of them both. Through my career, I had one handshake with this person, just meeting him briefly on a conference. Likely he doesn't remember me anymore, but I do. So we can model dye approximately by more broader potential because it has several like hydrocarbons, maybe even some little metal, and then at a shorter distance, it interfaces with acceptor of electrons, and we create the energized, excited electron localized on a dye, and we look for probability for this electron to be transferred from dye to semiconductor. These images, and I'll show the little modifications of the code. Those are very approximate. So this is dye, this is semiconductor, and here you see the probability of transmission is 10 to the minus third, but something is happening. Electron is tunneling. There is a way to do it by model, just doing these little modifications, or by importing the data on potential from ab initio. And I will start establishing contacts between class attendees and helpers just by cross-sharing emails. And then if you're interested, you demand. If they're interested, they will offer. And if nothing happens, then one needs to do models. But I think there were several class attendees interested in this electron dynamics. So let me bring in the part of the code, then invite everyone to do this little calculation. By the way, originally when the code runs itself, this line was not visible because it was masked and blocked by the, so this is a probability of transfer, which is quite small. But if I clicked on two other lines and push the line delete, then it expands axis around these two. Or I can manually plot only this line, or I can do the axis command to focus on a certain range. So for the dye, I just used width times 2. It's not like literal research work for peer review, but it approximately gives proof of concept that typically collection of atoms is localized electron in the broader range of space. So, and for the semiconductor, this was line 37. For the semiconductor, I did commented out the stuff that is on the right side of the cell. So I just put a % sign in the line 43. So those were two main changes: % in line 43 and increase of the width 2 times in the line 37. Huh? Yes, I added EZ, A sub Z to move it a little away, because distance, when the molecule is adsorbed to a surface, it rarely forms a chemical bond, or it is bonded through a linker which is not as conductive, and it is realistic to see that it's a little offset away. So please try these changes and run, and I will first walk in the class and then ask those online to share screen. Okay, so you have forward transfer and then back transfer. Yeah, it happens. It's between science and art to make these solar cells working. Even experiment and in theory as well. Okay. Yeah. Well, did you had success? Please share screen. I'll look what is going on. And no. So it is a different browser, right?
Yeah, it's a different browser.
Okay. So what I'm suggesting, not to download. It will be long.
Yeah, I don't know why it took me to the download.
I'm going to, if you permit me, I'm asking. Okay. So new line, and in the search, we are looking for not simply MATLAB and DSU, but CCAST. So running MATLAB on HPC cluster. And then there is a on-demand option. Then it will need your credentials. Are you working from home or from the lab?
Working from home.
Okay. Were you using university services this way before, or never?
I'm using the university service. Okay, let me just try to get in while somebody shares. Yeah.
Okay. Yeah, we'll continue. And now, Joshua, please share screen. Okay. Yes. Yeah. Works well. So no, stop. Keep it here. Do not erase. Let me request control, if you permit. So let's navigate to this figure, and now there is a little arrow you see here, edit plot. So we select it, and then click on the top line. And after that, there is either delete or backspace. Now there is another line at the top. You also delete, and then it automatically brings up this small probability transition. Make sense?
Yep, makes sense.
Okay. Okay. Yeah. Thank you. You can stop sharing. Sibel, would you like to share screen? Okay. So you have both die and two types of semiconductors.
Yeah.
Can you bring up your editor where you edit the code? Okay. So line 43. Let's put percent at the very beginning of line 43. Yes, here. Percent. Save and run. And it would be great to bring up the figure.
Hold on. Oh.
It didn't. Interesting. Sibel, would it be possible to could you stop and start sharing the? Oh yes, this way. Yes, excellent, excellent. Well, you do have this transfer lines. I'm just a little wondering why the part of the way this command didn't work.
Maybe my initial conditions. I need to modify it.
Yeah, you can. But
0.5. Momentum. See.
Save and run once again.
Yeah, hold on. I'll just.
Yep, erase all the things and then. Okay. Yep. Makes sense. Yeah, very good. You can stop sharing. Adam, would you like to share screen? Okay. Yeah, excellent, excellent.
Is it supposed to look like this?
Yeah, if you do not like it, you do not like how the reaction is going on, let's go, if you permit me to, thank you. So very small, and let's put electron literally in the molecule. Okay, save. And run. So in the previous version, we started electron right in the space between die and semiconductor, and it was very unstable energetic state that immediately split probability on two edges and did stuff which were looking interesting but not as realistic. Select, do it. Select, do it. Make sense? Adam? Do you have questions or do you approve what is happening? Your microphone is disabled, or you do not approve the things that is going on.
Yeah, sorry, I was muted. Yeah.
Okay.
I don't have any questions. Thanks.
Okay, yeah, you can stop sharing. And what you did right now, I know that you have selected the exploration of charge transfer, but this is too detailed mechanistic thing that happens on a very quick femtosecond time scale. The processes that your group is researching is focusing on a longer time scale when this transfer has already happened, and one focuses on how the charge transfer depends on vibrations on the interatomic distances. So it is advised that you use slight different modification of the code. So I'm going to put a car in front of a horse and immediately jump to section C, because in all previous years I was delivering it too late, and everyone who selected section C was like suffering. So if no one objects, I'll just offer we all do a little demonstration, and I'll start speaking about it, putting seeds of thoughts. And in preparation to next week, probably we will make many interactions one-to-one to have everyone equipped with codes and helpers and ideas. But I'm going to show something that I will not be able to communicate by email. So it's not super complicated, but much easier to deliver in person. And I'm going to, so this can be erased. So the potentials, which are much more precise and related to real life, can be borrowed from helpers and read. You already know how to read variables and arrays from the file. So one can download a file from helper, put it on the same directory, and then read variable v, like v equals load and then file name. Make sense? I have a template with this command if it is too much, but this is like standard and easiest thing. Closing. Closing. And yes. So I'm going to open and run the code that I did send to everyone. That's WP Marcus. Open Marcus. This code is, let me double check the choices. So this version of the code is advised to Adam, to Nate, to Mai, and to Lola. So I think it will be most populated. And Sibel, either during the week or first thing next Wednesday, I will focus on this interatomic distances and dedicate things to your project. I'm going to.
Sounds good.
Huh?
Okay, sounds good.
Okay, yeah, thank you. It will be in some sense easier. I just want to cover this really challenging, well, not super challenging, but something that needs special words and in-person interaction. Yes. So it's better to run right away and then discuss the code as we go through. So current version that is uploaded does have n tau equals 100 because we all are humans with limited patience. For better images and more interesting science, it's better to have it bigger, but do not rush to do it. If you increase it by 15 times, your patience could be expired. It may run like 10 minutes instead of 30 seconds. Run first without increase of this time. I'm going to launch it and then chat as it runs. The important thing that mass, before it was 1 in atomic units, now it is it should be substantially bigger number, at least 2,000 more of the, if we are speaking about proton. If it is heavier atoms, something different. Okay, and it is immediately using writing the video to the file. Okay, enough speaking. Let's run. And that it should request to push the okay, so it is my most favorite thing. So let's just watch and observe. Instead of 1 potential energy surface, like harmonic, we do have 2. And it corresponds to the fact that 1 potential red here corresponds to ground, blue corresponds to either excited or different electronic states, for example, with charge transfer. The x-axis does not mean position of electron. It is elongation of interatomic bonds. So in this picture, we do not have transfer over like 10 angstrom. Even if it happens, we monitor how the interatomic distances in a molecule or in some molecular system responds to instantaneous transition of electron. So it means the bond length, atomic units, is like twice bigger than angstrom. So 5 atomic units means 2.5 angstrom, which is like typical bond in solids. So we see how interatomic bond changes by less than 10%, less than 1%, right? If you excite or contract, and there is a probability distribution. When we started this simulation, we started in the excited state, blue potential and blue wave packet, right? There was no red wave packet at all, right? But since we have a probability of transitions between blue and red electronic states, there is a chance that there is appearance of this red wave packet, right? So there is like water between 2 cups. It comes from 1 cup to another and then back. And by electron migrating between these potential energy surfaces, it explores different eigenstates. Since potentials here are chosen to be harmonic for simplicity, one can do something more exotic. since potentials are chosen to be harmonic, the even with dynamics and particular solutions, there is a chance that a system prefers eigenstates. And you see that for the red potential, system really likes the eigenstate with 4 humps, which will be like 0, 1 hump, first 2 humps, second 3 humps, 0, 1, 2, 3, third eigenstate of oscillator, right? In the excited, in this blue potential, it looks like a ground state. There could be something more additional details. It oscillates. Maybe it's more related to coherent states that we are studying right now in the class. But there is a simultaneous motion between electronic degrees of freedom and nuclear degrees of freedom. Do you approve that image is not too complicated and can be intuitively analyzed, right? The equations and ideas behind it are a little bit more challenging, and I believe complete picture of equations behind it will be the very last lecture before we do presentations. I'm going to give fine details of everything, and it will be like top point of the class. So it's an advanced subject that relates to many practical problems of physical chemistry. But to enable opportunities to go forward to those who selected the subject, we're discussing it right now. So the practical question, if we accept this general picture, is how to select parameters. So what is the equilibrium bond distance for red state and blue state? What is the curvature of parabolas? Are they the same or slightly different? What is the offset? So it's like, what is the energy of this excited state compared to energy of ground state? What is the mass of this oscillating bond? What is the initial state? If these parameters are inserted correctly, then one runs and then gets some observables. So which observables one can extract and analyze? Same way as we did before, one can look for probability of the transfer. So what's the probability is that blue converts into the red? And the image that comes here basically gives this probability of transmission. So originally everything is in the blue, and then it appears in the red. The rate, how quickly these things are changing, the slope of this curve, is the rate of reaction or rate of electron transfer in so-called Markov theory that was awarded by Nobel Prize in chemistry. And this rate of charge transfer is likely the main observable for Adam in his undergraduate research. So the molecule, this parameterization of two parabolas is very universal, and it is applicable to like almost any molecular system. And slope of this, how quickly population in the acceptor state increases, is something that was of interest to like generations of chemists. If you run this code, you'll also see this wallpaper decorations. So how to interpret them? So Joe was teaching us how to analyze vibration in of harmonic oscillator if there is only one potential energy surface. And if you remember his image, it was something oscillating forward and backwards, right? Distribution. Here we are plotting distribution in blue parabola and in red parabola. So as time passes, originally there is only blue, and as time passes by, there is additional probability distribution appearing in the second parabola. And here one can just use negative and positive to scan over all colors, because they are different things. Or one can add them together and plot in a single color distribution. Okay. So maybe before I get to any parts of code, let me invite you to run it, and then I'll watch if you can healthy just operate and make sure it runs on your equipment.
You do it at 100.
And to practice your passion, not to practice your passions, I suggested to use 100 instead of like 2000, which will cover only initial stage of the reaction. If you come back and use like 1,500 time steps, it will go further. But just be prepared that it may take longer time. Okay, yeah.
I didn't do this
Since you're planning to do something different for the project.
I was doing
Oh, okay, but you can still run it as a like educational component, and I'll stop by when you'll be ready. I am going to stop sharing. Lola, do you have any progress in making these codes running?
I don't know. I think I'm not doing something right.
Okay, it looks like something is working, but you are running the code that is so this photon echo, P echo, is a code for Joshua, who wanted to do NMR.
Oh. I'm supposed to run this one.
No, it's also movie block is also for Joshua. These two codes.
So I'm not sure which code I
There was a code WP_Marcus.
When did you send that? I didn't.
And I was also sending it to you yesterday before the whole.
Oh, yeah.
Did you found it?
I'm looking through my email because I didn't save it. Yeah, I already found it.
So if you found and if it is active and you're ready to run, please share screen so that they see what is going on.
Yeah, I'm just opening it up.
Yes, this one. Open with, maybe open with MATLAB. Let's go back to the email and save. Maybe just say, do not close MATLAB. It's just what it is. You already have it. Wait. No, please come back to the file browser. So it is class Chem364 Lab research. Now let's go to MATLAB and navigate to the same directory. Research. Double click.
I don't know why it's not doing anything.
Okay. Now let's check in the MATLAB command window that nothing is running right now. Okay. Lab research. And now we can try to run this code. Okay. You see it moves a little bit, right?
Mm-hmm.
And you see the red thing appears here, just grows as blue moves from left to the right. The red wave packet increases. So the length of simulation is intentionally, so it does much less than full period. It just maybe 10% of a period moves a little from left to the right. But if on continuous simulation, it will oscillate. And here, the yield of reaction just slightly goes, maybe from 0 to 3%. So everything works well on your side. If you are curious, you can change the number of points to a bigger number, save, and rerun when you're ready. But everything goes well, you can stop sharing.
Thank you.
Yeah, thank you. Joshua, would you like to share screen? Just okay. So to see the things more spectacular, I'm asking your control just to be quicker if you would like to provide it. So if you go to the very beginning of the code and change number of time steps a little bigger, save and run, and you will see a little more spectacular demonstration. But I see it works well on your side, so you can stop sharing and just enjoy how it works. Sibel, would you like to share screen? Okay, excellent. Yeah, I see proofs that everything works in a favorable way on your side. You can stop sharing. Adam, would you like to share screen? Okay. Yes. So do you have any comments? How do you interpret what you see?
I mean, I see how I guess that whatever the blue distribution sort of thing makes these this wave packet here propagate.
Mm-hmm.
I'm not sure how to interpret it though.
So originally there is only blue dots and dashes wave packet, and the thin red is 0 at initial time, right?
Mm-hmm.
So, but as time goes by, blue becomes smaller and red becomes taller, which corresponds to slow, continuous electron transfer from donor to acceptor.
Oh, okay. That makes sense.
Okay, and you are very welcome to discuss it with your group members and with an advisor. And also, I don't know how busy your schedule is. If you have tons of free time, look in Wikipedia or about so-called Marcus theory. It's really quite boring, and it has more details than we need today, but just to get general ideas for your project.
Okay. Is there anything over here that I should change to get kind of a better?
Okay, so let's quickly go through, just not to affect interests of others. So I'm going to request edit, so we can, if you kindly give it, we can just progress a little quicker. So initial momentum corresponds to temperature, and there is a formula connecting like kBT and momentum like equals momentum squared times mass divided by 2. So line 8, delta energy offset is energy difference between donor and acceptor. If you are speaking about charge transfer or ground to excited, if LOA is using for luminescence. But this parameter is important, and you will need to find its value and change it.
Okay.
Nuclear reorganization. Well, you may need to change it, but also you will need to learn a little bit, like what is concept of nuclear reorganization and in which units it is measured. And I think it is enough to start. We can go with more details, but look through, read, and chat either to your group or to me, and we'll go further.
Okay, sure.
There are some other parameters, but I just do not want to overload you with details.
Yeah. All right.
And do not hesitate to contact in the middle of the week. We need to clear it before next lab.
Okay, sounds good to me.
Thank you. You can stop sharing.
Okay.
So we are about done because time is out, but I want to do an absolute top, absolute how to say, maximum of what we can do in this class. So right after the Marcus dynamics was run, I want to immediately in the same directory to run the code that I also sent, which is named states eigen. States. So this code would not work standalone, but lecture number 43, just before your presentations, I will be mumbling about it for at least 50 minutes. So it's only visual thing that we will be analyzing later, but I can just bring a little bit for your curiosity. So it is the same blue and red parabolas, and each of them has its own eigenstate, right? That we just learned a couple of weeks, because it's harmonic oscillators. And then there are, this model can be used primarily to describe electron transfer, but at the same time, absolutely same parameterization works for photoluminescence in molecular systems. Both electron transfer or optical transitions, we go from blue to red parabola, but we need to match resonance conditions between not only electronic states, but also vibrational states, right? So one can get transition from one eigenstate to another eigenstate. And it is interesting that ground state for the blue parabola, this one, is very close in energy with third excited state of the lowest parabola. Therefore, if we prepare system initially in here, it will resonance with transfer to another state, right? If we start from the ground state in the lowest parabola and then use light to promote it to another electronic state higher up, one would need to see that this eigenstate has spatial overlap with the target eigenstate. So the optical absorption will happen not at the energy differences between initial and final electronic energies, but it will use substantial offset to have a spatial overlap of the vibrational wave functions of the initial state and final state. Therefore, absorption will happen at much bigger energy than offset of electronic states. So this property is responsible for so-called Stokes shift, and it is observed in like vast majority, almost in any molecular dye. So if you want, you may try. Oh, yeah, and here is absorption spectrum. So it has, although it is only 2 electronic states, there are like 20 transitions for different pairs of vibrational states. So feel free to run it and report if there are any problems. But I think time is out. So formal part of the meeting is ended, adjourn, dismiss. But I'll happily stay here and answer any questions. And please do not hesitate emailing me. We need to do some after-class activity on one-to-one basis to make sure your projects are going forward. Lola, Joshua, Sibel, Adam, do you have any questions to discuss right now?
No.
Okay, yeah, then feel free to, if no questions, feel free to disconnect and adjourn. If there are questions, stay here and formulate them. I will be at your disposal. A little competition. There will be a conference in Florida in mid-February with abstracts due last day of December. So best projects from this class can be sent there, and organizers of conference will partially compensate travel. It's not the goal of the class, but if you want to get away to the beach, it's one of the opportunities.